Hello everyone, today we will be going over queues today, and without any further hesitation, let's get started. So queues are considered a type of data structure that will be treated as the opposite of a stack. For stacks are typically known as a series of a stack of plates, metaphorically speaking, but queues on the other hand operate based on the structure of first in, first out, and can be thought of in a similar metaphor to a line in a roller coaster or a line in a grocery store aisle. When one is checking out, there's always that one element that is already stored first, and it will be the first one to go out, unlike a stack where we would need to actually see what is at the top of a stack and then go through accordingly within that data structure. But yet there are still some key similarities between a stack and a queue, mainly the push, pop, and peek functions that are already ingrained inside of a queue are luckily very similar to a stack. It's just the order of the way how queues operate in general. And so if we were to go over our example we have over here we're going to have a queue of integers, and then we are going to push elements, namely 10, 20, 30, and we are going to be outputting the elements that are directly inside the queue. And we see in particular from the direct output 10, 20, 30. While in a stack, it would have been the complete opposite of 30, 20, 10. Queues, on the other hand, as mentioned before, operate by first in, first out. And also for further clarification and clear up any confusion or misunderstanding, typically when it comes to queues, people would like to actually interchange the names for push, pop, and peek as well. For NQ, DQ, and front element, these functions, just by the names, behave very similarly to what the queue's intentions are. As long as the logic is fully there, then there should be no problem. But again, just for context, these names are technically interchangeable, but for context and full awareness, it's best to be able to use NQ and DQ, but you can also use push, pop, and peek. And we will look at these examples within our problems. And they're really efficient as well. As stated before, they have a similar space and time complexity of O of 1 for time and O of n for storage in general. And without any further ado, let's move over to our problem. And now let's go over our practice problem. So our practice problem states that we need to implement a queue using an array and then a linked list and perform the following operations. First, we need to enqueue, which is also indicated as a push. We need to enqueue an element to the queue, we need to dequeue an element from the queue, and we need to check at the front element of the queue, which in of itself is another variation similar to the context of a stack with push, pop, and peek, except for it's NQ, DQ, and front element. These are the three components that we will do, and the structure of the queue is different. For it goes first in, first out. Stacks go last in, first out. Stacks equal LIFO, queues equal FIFO. And finally, we need to check if the queue is empty. So, first thing we're going to do is that we are going to build our queue from an array. Let me just move this over here. Here we go. And feel free to code along as well. Let me just put this right here for our requirements. All right. First thing that we will always do is that we are going to include our libraries, which means that we're going to include iOS Stream, and you can also do this on Visual Studio Code as well, or any other text editor, and then we'll use using name space std. Then I'm going to make a class called queue, and don't forget our int main function as well. Our class queue is going to have the following: int front rear size. Since we're going to be dealing with an array, so array queue, array based queue, there we go. Then I'm going to put in a max, which will be a static constant integer of max size equal to 3. We're just going to put in 3 different elements on the inside, and I'm going to fill up the array with our max size. What do I have this here? Oh yeah, that's right. Here we go. Now, next part, I'm going to have a public instance, and I'm going to first initialize a function that we have. We have queue front. We're going to initialize the front, rear, and size. But the way how we're going to do that is we are going to put in 0. Rear is going to be -1, and the size is just going to be 0. For we have an array, and arrays always start with 0, which is why we have a rear at -1. Our front, since there's nothing already in, it's going to be at the 0 index, and our size is also going to be at the 0 index as well. So this is how we first initialize our Q array, or our array-based Q. There we go. Now the first part, I'm going to put in the functions NQ, DQ, check front element, check is empty, and I'm also going to have a function to print out results. So NQ is going to be the following. We're going to have a boolean first for NQ, and we are going to put it in our integer value since we have an array based in integers as indicated right over here, and our max size here. And we will check if the size is greater than or equal to the max size. That means we cannot add any more, and we're going to have a stack overflow, but I'm going to call this a queue overflow in this case just for indication. Always check for edge cases as well. That's always the first instinct that we have in mind. And L. And then we will return false because we are dealing with a queue. And otherwise, if the size is greater than or equal to the max size, we return false. We return false. But if not, that means we are going to add in an element inside of our queue. And queues operate in, first out, which means we're going to go to the rear at the very beginning of it, and what we will do is that we are going to put in one element forward based on the max size with respect to it, array rear equals x, and we're going to increment the size as so and return true, indicating that we have already added an element on the inside. Now this is just one technique that we can do. There are different techniques that we can also go through as well, but we're just focusing on the different variations between front, rear, and size in respect to all of the different components of the queue. Now, the next part we're going to be doing is a DQ. Now I'm going to put an int DQ in this, and if the size is less than or equal to 0, we're going to count the queue underflow because it's saying, hey, there's nothing in there. First, these series of techniques are very similar to what we did in stacks before in the previous video, if you happen to catch on as well, just for further context. And we will return 0 since we have an integer in this case. And if the size is within the range and not less than 0, that means that there's an element that we can get rid of. So int x equals array at the front, because in order to DQ, we always go for the element in the very beginning because of first in, first out. And that means the front is going to be equal to the front plus 1 with respect to the max size, similar to what we did over here, except for the difference is that we're kind of doing the opposite. And we also need to make sure that we spell everything correctly. And size will be decremented, and then we're going to return x. So that's how we do DQ. And now we need to check the front element, which is also known as a peak in stacks. So in order to check the front element, we're going to do int front element. This is how we're just going to call it. And if the size is less than or equal to 0, we can say Q is empty, and L, and we're going to return 0. Otherwise, we will return the front of the array, because that is what we're looking for. So we always go with our edge case first, and then we'll return the actual front. And we return 0, kind of like in the similar context of what we have for our Boolean as well, where there's true and false, except for we have integers in that case. Alright. And then the next part, we're going to check to see if it's empty. So we're going to do a Boolean condition is empty. And that means there are no elements whatsoever. And technically, Booleans are already set to true. So all we got to do is that we need to return true if the size is equal to 0 indefinitely. It is indefinitely equal to 0, hence the double equals right over here. Now, I'm going to create a function to be able to actually print out everything. And I'll also make this to calm this down. I'm going to call this function void display. And that can be called upon within the whole queue class that we have. And this void display is going to have if the element is, or if the queue is empty, we can just say the following: queue is empty. Empty, sorry, frowny face. There we go. And then otherwise, we don't need the else statement for the sake of time, but you can. But to make things efficient, you can just put in the for loop, just save on time, for int I, because what we'll be doing is that we are actually printing out all of the elements in our array that we've made for our queue. So that means we will use a for loop to scan throughout the rest of the array. So we'll have a for int I is equal to front, I less than or equal to rear, and that means we're going to decrement through the rest of the loop as well. So we go plus I, because we're doing first in, first out, starting directly all the way from the front and then incrementing accordingly until we get to the rear because of first in, first out. And we treat everything accordingly between respect to the front and the rear. And that means we will output count array index of I to be here for each step and component. There we go. And now let's test this bad boy out. So first thing I'm going to do, I'm going to have an instance of queue, call it queue. Then I'm going to do a queue dot. But let's look for the function that we did. And it looks like we need to put enqueue right here. I'm going to put 10. And enqueue always means pushing element. And let's go 20 and 30 because our max size is 3 that we have already stated. And then I'm going to do a queue dot display to test everything out, make sure that we have our whole queue. Then I'm going to output queue dequeue since we need to pop an element, and then element has been popped. I'm just gonna put this right here. Yeah, there we go. And then we're gonna call upon the front element, check at the front element, which means this is the front element, queue.front element, call upon that function, and then we'll end that line, and then count finally updated elements in the queue. Queue.display is indicated, and since we have an integer, we would have to return 0 as a base edge case. And I don't see any errors whatsoever. Let me just zoom out of here so you folks actually see what we're dealing with. Notice how we have our class queue, public, enqueue, dequeue, front element as indicated based on the problem. And we also have queue is empty, and then we have a function to be able to display everything. So now let's run this. And there we go. So we have 10, 20, and 30 as our queue right here. Then the next part is that 10 has been popped already. Because one, this isn't a continuous display that we have here, so technically that would be, if I just put -n right here and we run this thing, should be able to separate. There we go. 10, 20, 30, and then we already have 10 element has been popped, or sorry, has been popped slash dequeued. We can do that again. Yep, element has been popped slash dequeued. This is the front element, which is 20, right here, and then the update elements of the queue include 20 and 30 right here, because we have the /n already set up in place. And finally, we already did everything. So this is the array component. This is an array-based queue, and so yes, I will put this in the comment section. Feel free to take a good look. Let me zoom out of it entirely. I just got this in 4K, so there we go. There we go. Feel free to take your time. And now let's focus on developing a queue using a linked list. And now let's go over and build our queue from a linked list. So in order for us to be able to go about this, first thing we always need to do is that we also need to include our library. So we'll have include iOS stream in this case, and we will be, as usual, using namespace std. So first thing we're going to do is that since linked lists are comprised of nodes to be able to start with, the way we're going to build this is that we're going to go, let me just create our class first, and let's create our node using a struct queue node, and then int data, indicating the type of element that'll be going inside of our nodes, since linked lists are comprised of chains of elements altogether. And we'll be doing a singly linked list because it is considered more efficient in queues and stacks, since it's going in one direction rather than just going back and forth, considered in doubly linked list, and we're looking for a specific type of element. If you're using in the context between the two different lists, most likely when building stacks and queues, focus on singly linked lists by general principle. That is what is more conventional. But anyway, focusing on queued node right here, we're going to initialize our node. And the next part, what we're going to be doing, queue node for the front, and then queue node from the rear, because queues typically have a front, rear, and front and rear. Since we have the last element on the very end and the front element as well. Now I'm going to have a public instance, and I'm also going to put a semicolon here. So public initialize our class queue. This is how we initialize. So front, null pointer. We use null pointers for linked lists in general, and then rear, null pointer. Sorry about that. Now we're going to enqueue, dequeue. We'll check the front element, and check if empty, and then I'm going to have a function to display, much like we did before. So first thing I'm going to do with the enqueue is that I'm going to have a function in this case. So linked lists are widely good for functions. Well, I mean, typically throughout the series in particular, we've been using void to be able to indicate the type of function you can use. You can use an integer, a boolean, or a function. Right now, I'm just showcasing the different diversity of functions that you can use depending on how you want to be able to build your queue. So in this case, we'll use void enqueue int x queue node, new node is equal to new queue node, since we're calling upon the function over here to say, hey, let's create a new node in this case. Don't forget your semicolon. And if we don't have a new node, what we will be doing is that we are just going to say, hey, we can say Q overflow as an edge case, and L. And we can return just nothing right over here as a base case right here. So we just have return as a placeholder. Now, for us to be able to connect the new forms of data, we're going to have new node connect with data be equal to x, which is going to be considered an integer that we have. And we'll have new node next indicate as the null pointer just to initialize everything and make sure the chain has already been built up. So it's moving from one point to another as we are in queuing our entire queue. Now, that we have already initialized x over here and have our null pointer, we'll be doing this for the rear, and then we'll be going for the front. So for the rear, if we are putting in a new node directly from the rear, we'll have rear next because of first in, first out, and indicate that as a new node. And then we set the rear to be the new node because of first in, first out. And then we'll have front as well as an edge case to indicate if it's not at the front, whenever we are in queuing or dequeuing, then we're going to make the front be declared as the rear because of first in, first out. FIFO, as always. Now, next part, we're going to be dequeuing by using an int dequeue. And if the element we were looking for is not in the front, or if there are no elements really, we're just going to say Q underflow and L. And since we are dealing with integers, we'll have return -1 in this case because we're doing a dequeue, and then we'll have Q node temporary by doing a swap technique. Swap techniques are widely popular for linked lists. Front and then will be equal to front next, and then if there's nothing directly at the front, we're going to be doing the opposite and go rear equals null pointer, and then int dequeued is equal to temp data, and then we'll delete the temp and return our dequeued, indicating the exact element that we have dequeued throughout the rest of our queue. Now we're going to check the front element, and the way we do so is going to be the following. So this time I'm going to put an integer in this case. I'm going to call it front element. And if the element that we are going for is not the front and is not there, we indicate that the queue is empty. Then we'll have end L. And finally, return -1 because we're dealing with integers. And we'll have return front data. So we're getting the exact data inside the front element that we have because we're dealing with a linked list. And I'm going to check to see if this is empty by doing a Boolean condition. Is empty, and that means we return true in this case if the let's say the return front is equal to null pointer. Mainly because since we are dealing with a linked list, we have to focus on the chain really compared to the previous iteration that we have for our array, because our array has a fixed size of elements. That's why in particular for size it would be indicated as 0, but since we're focusing on the data in of itself, the logic would be different, immensely different in this case. So actually I would get rid of these parentheses over here. Since we're dealing with the chain of elements already hooked up together and linked lists are comprised of a head and then a series of nodes to follow through, we always check the front element first, indicating if there's nothing there. If there's nothing there, then therefore it is considered empty. And then the function to display, I'm going to go void display if is empty. elements frowny face because it's funny. And then I'm gonna have Q. You can always return for function just by good principle. Then Q node temp is equal to front, and since linked lists always start with the head and a series of nodes, we go with the front, and then we're going to output all of the elements on the inside of the linked list. So that means we will be doing temp doesn't equal null pointer, because we're going to be checking the next iteration for each one. For we declare temp as the front, and therefore going through each one. While temp is not equal to null pointer, that means we are going to get the data specifically inside of the linked list. Data. And then we'll have temp equal to temp next. And then count end L. Actually, you can just leave it as that. Or you can just do this. Yeah, that should be fine. Yeah, actually by good principle, it should be good right here because we are dealing with the front element first, and then we're printing out the rest of the data accordingly until we actually reach the very end. So it's good principle to be able to have this. All right, now we're going to test this bad boy by int main. First thing we're going to do, declare a class. We're going to enqueue, display, pop elements from the queue, and further display. So we declare a class by doing queue. So this is what we call. So we're going to have queue dot enqueue. I'm going to put 10, 20, 30. Then we'll display. So I'm going to do queue display. Then I'm going to pop an element from the queue by doing count. Popped, or I should say dequeued, element from the queue. Queue dot dequeue. And now count queue dot front element is our front element. And for the display, for elements in the queue, queue dot display, return 0. Let's build this and make sure this works. All right, and see the errors right here. Feel free to take a screenshot of what we have done. I'm going to go slow for a second. All right, now I'm going to run this. Yep, so we have 10, 20, 30, dequeue from the element, looks like 10, that's right, because it goes from the front. 20 is our front element, therefore, and further elements that we have in our queue are going to be 20 and 30. And it looks really efficient, looks very clean from what we have already done. All right, so yes, indeed. This was our queue-based, well, this is our linked list queue. Yeah, linked list-based queue in general. And so, yeah, this looks pretty good. Just get right here. There we go. Hey everyone, thank you very much for taking time to watch this video. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions as well, feel free to put it in the comments section. And as always, take care. Cheers. Bye-bye.